Hey guys, Mr. L coming back at you with another video, and in this video we're going to talk about kinetics. So we're going to talk about the speeds of reactions and some things that go along with this in terms of how kinetics is affected by concentration, temperature, the presence of a catalyst, and the different phases they're in. I'm going to show you how to set up a rate or a rate law, as well as we're going to see how stoichiometry changes the rates of products and reactants. So let's get into this video. So the first thing we're going to talk about is the idea of kinetics, or the speed of a reaction. So if you recall from a previous video, just because something will occur doesn't tell you how fast that it's going to occur. So if you don't remember what Gibbs energy is, or delta G, go back and watch a previous video. So if our delta G value is negative, meaning it's spontaneous, it will occur, that has nothing to do with the speed. So in these videos, we're going to start talking about the speed of a reaction, or the things that will affect the speed. So if we've got an example such as diamond will spontaneously degrade to graphite, but this will take a very, very long time occur. So just keep in mind, just because it's favorable doesn't mean that it's going to happen. So there are going to be four big things that affect rate. The first thing that's going to affect rate is the phase of the reaction. So if you're in the gas phase, the particles are going to have the most entropy, the most randomness, and we need particles to smash into other particles in order for bonds to break and new bonds to form. So the more random the phase is, the more likely it's going to react. And if it's in the gas phase, it's going to have higher kinetic energy than if it were a liquid or a solid. So generally the gas phase is the fastest phase to react, as well as if everything is homogeneous, then it's generally quicker. So if you have something like a solid, like a tablet, you're going to want to crush that tablet up into a fine powder to increase the surface area in which particles can smash into the surface area of that powder. The second thing that will affect rate is the concentration of the compound. So if you've got more and more of the compound, then you have more and more likely that that compound will smash into whatever the other reactant is. So higher concentration is directly proportional to higher kinetics or higher speed. The third thing is going to be the temperature. The temperature, higher temperature, is going to be more molecular movement, more kinetic energy, so it's going to have a higher likelihood to react, overcoming the activation energy barrier, which we'll talk about in a later video. And then the last thing is the idea of a catalyst. A catalyst could be an enzyme, like a biological catalyst, or it could be a metal like platinum inside of a catalytic converter on your vehicle. But what a catalyst does is it helps to orient particles in a very specific orientation to allow the reaction to occur. So if two ends of a particle need to come together, the catalyst is going to aim those pieces right at each other, and there may be some enzymatic cofactor or some charge distribution that will help aid bond formation and bond breakage, lowering the activation energy. Catalysts are also recycled. So you don't use up the catalyst in a reaction. Whenever you use the catalyst, it's going to be available for the next reactant to bind to produce the next product. The next thing we're going to look at is how to set up a rate. So a rate is equal to the change in something over the change in time. And remember, delta is always final minus initial. So you're going to have a final value at some final time point, and then you're going to subtract that from some initial value at some initial time point. When we're in chemistry class, the thing we're interested in changing is typically the concentration of a reactant or a product. Either we're going to use up the reactant over time, or we're going to produce the product over time. So we generally use brackets. Whenever you see number inside of brackets in chemistry class, that means molar concentration. Remember, molarity is the amount of moles per liter. So we're going to see the change in concentration over the change in time. We may also use pressure data. If you're performing a gas reaction and we can see the change in pressure, we can equate that to a concentration. So you're going to have three different rates that you're going to solve for. You might have average rate, which is just say from 20 seconds to 40 seconds, how much does the concentration change? That's pretty straightforward. So you would set up the change in concentration, final minus initial, over the change in time, final minus initial. If we're talking about instantaneous rates or initial rate, now we're starting to get into a little bit of calculus. You won't need to know calculus how to do this, but I'm going to teach you the idea of a derivative, or the first derivative. So over time, you're going to use up your reactant. So if we're going to have some reactant, we're going to use it up, it's going to be a curved line over time because we're going to have less and less reactant available to react. So to find the instantaneous rate, or the speed at that one single time frame, you're going to try and draw a straight line tangent to the curved line. And then from that straight line, you're going to find the slope of that straight line. So you're going to have a steeper slope closer to time 0 because it's going to be the fastest speed at time 0. Then as time goes to infinity, that line is going to become flatter and flatter and closer to a 0 slope. So this is your instantaneous, or the first derivative from that curved line. The initial rate is the instantaneous rate at time 0. So it's a special one. All you're doing is doing this at time 0 instead of 10, 20, 100 seconds. It doesn't really matter. So just keep in mind that the curve is going to be going slower and slower as time goes on. So the instantaneous rate, or the first derivative, the line tangent to the curve, is going to be getting flatter and flatter as time progresses. So in order to do kinetics, or analyze rates, you must perform a reaction. So you're going to have some way to detect a reaction, and maybe it's a spectrophotometer. So you're detecting light absorbance, or transmittance, or a color formation, or pressure value. You're going to have to detect the rates at which something forms or is getting rid of. So that's the first thing you need to do, is the detector. The next thing you need to keep in mind is we need to record data. So if we're looking at this data for the production of butanol from chlorobutane, we could see that at time 0 we've got majority of our chlorobutane, and as soon as that reaction proceeds, the speed is going to be highest. Then as time goes on, the speed of the reaction is going to get lower and lower because we have less and less chlorobutane left in that reaction vessel. So the last thing we're going to look at in this video is how stoichiometry dictates the amount or speed in which something is formed or something is used up. So if we're thinking about our chlorobutane reaction, one particle of chlorobutane is going to be used up, and you're going to produce one particle of butanol. So the rate at which chlorobutane disappears should be equivalent to the rate at which butanol appears, since it's a 1-to-1 ratio. Whatever this one goes down by, the other one needs to go up by the same speed. Well, what if the stoichiometry of the reaction isn't 1-to-1 like in this example? So say we've got 2 moles of ozone decomposed to form 3 moles of oxygen gas. Well, the way that you're going to equate the rates is rate is going to be equal to, then you're going to set up a fraction. So if the coefficient on ozone is a 2, you're going to put 1 over the coefficient. And since ozone is being used up, it's going to be negative. So you're going to have equal to -1/2 the change in concentration of ozone over the change in time. And that's also going to be equal to the formation, so it's going to be positive 1/3 the formation of oxygen gas over time. So you could start using your stoichiometric coefficients to use as fractions to solve for one of these things or the other. So there it is, you guys. There's the video on kinetics, how kinetics is affected by 4 major categories, how we set up a rate expression, what's instantaneous rate versus average rate, and how stoichiometry will affect the rate. So if you enjoyed this video, smash the like button, subscribe, send it to your favorite Star Wars villain, send it to your favorite Korean side dish or banchan, and we'll see you in the next video.